Okay, so continuing this on, thanks for hanging in there. Again, going through slow, you should be able to do this quickly. At some point we said we derived the equation for the range, which we often implicitly mean assuming that it ends up here at the same height that it started, so that delta y is 0. We got the range equation. Don't memorize it. Make sure you can derive it from the beginning. It's not too bad. Just take it one step at a time. It's hard at first, so you got to push yourself. We derived this, and we said that the same complementary angle will land, for complementary angles, will land at the same place. Okay, so let's sketch that over here. So what I've drawn here is, I've just chosen two, people often do 30-60, you can do 20-70. I did 21-69 just to be different here. Remember that we're going to project it at the same speed, otherwise it's not fair. And if we look at this, how far it goes horizontally depends on how fast it's going horizontally, right? Critical that this is the horizontal component. And how long we are in the air. Now if we look at this trajectory, we can see that this guy is going to go and head on out, right? And this guy, landing at the same place, though, is going to go, it's going to peak in the same horizontal distance, halfway, and come down and head down that way, right? All right. So what does that tell us? Well, let's see. If I lower my projection, reduce my angle, then I'm getting more of my velocity directed horizontally. And so if the angle is less than 45 degrees, what I'm getting here is, in this case, more of my velocity horizontal. If I go up here, I'm not going sideways at all, so Vx is 0. So it's going to be, in this case, less velocity projected horizontally. So we're going, hey, wait a minute, that's looking pretty good. But of course, the key factor is the time. In which case is the object longer in the air? It's clearly not the same time. If you're playing baseball and you're throwing someone out at first base, you don't really want to throw the ball this way. Your teammates will be upset with you. It'll take longer. So this is going to take longer time, right? And a shorter time on the green path. So they won't get there. They'll get to the same place, but they won't get there at the same time. If you project them both at the same time, green will get there first, obviously. Okay? So that means that here, the green path will be less time, whereas the pink path will take more time in such a way that it's perfectly balanced. Okay? In fact, we look at this, we can see that the equation for Vx was V1 cos theta 1. And in this case, a smaller angle makes that more. And the equation for time was 2 V1 over G sine theta 1. And here a smaller angle means less. Exactly in a complementary way. And the product gives us the formula. So we can also see this just looking at the time. If you look at the time, same velocity, that's all the same. But angle. For sine theta, if we have a bigger angle, then we have a bigger sine theta. If you got a bigger sine theta, you've got a bigger delta t. And that's the way you want to think. All right, so it makes sense, actually, that you're going to land, for complementary angles, you'll land at the same place, assuming negligible air resistance, no propulsion, etc. And you'll land at the same height, delta y is 0. So that's a nice result. We can explore this result even more. Suppose I want to look at how far I go if I land up higher. So this is going to land short here, and this is going to land long here. But what if I land lower? Well, this is going to land, now my large angle is going to land short. Here it lands long. Here it lands same. Here it lands short. And this guy is the one that's going to win here long. So for example, you're doing a shot put, and you do a shot put like that. It looks like, from this model, it looks like I'm going to want to push the shot put at less than 45 degrees if I can get the same speed. Now here's where real world comes in. Getting the same speed this way versus this way might be different. Muscle, bone, mechanics, right? We need folks that know about that stuff to help us. We need coaches. We can model it. We can take video. We can analyze just the right angle that's going to maximize our range and get us that gold medal or whatever. So, you know, this is a model assuming this, but in the real world, throwing a shot put at different angles can affect your V quite a bit. Given the same velocity, if I land lower, then the lower trajectory will go farther. All right, cool. And you can explore that here mathematically. Just think. Don't look for simple memorization. Now let's go over here, finish this off. We might want to maximize the range. You say, hey, the range. Let's see what angle will give me the greatest range given a certain speed. So I maximize the range being the delta x, assuming that I land at the same height it left, or doesn't have to land, it could keep going, but for that. Obviously, if you throw it faster, it's going to go farther, so we're going to keep that the same. That's the same. So how do we do this? There's two ways. It's kind of cool. Here's the range. Delta x 1 to 3 is 2v1 squared over g cosine theta sine theta, whatever. Don't have to memorize that. The trig identity is useful, or we can use calculus. There's two ways. So one is that that's equal to v1 squared over g, which is going to be the same for us, times the sine of 2 theta 1, because 2 cosine is that. So let's explore that one. It won't take too long. So let's check that out. When is that maximized? I got delta x 1 to 3 equals v1 squared over g sine of 2 theta 1. Well, that's maximized when this is the same, right? So the maximum of that. Well, you know the maximum of sine is equal to 1. So write it out. Every time you have a thought, write it. I don't know, where am I going? I don't know. It's the first time going through, you don't know where you're going. So that means that's equal to 1. Oh, wait a minute. Sine of 0 is 0. Sine of 90, or pi over 2 radians, is that. So that means that that has to be 90 degrees. And that means that theta 1 is 45 degrees, as you might have expected. Yay! I mean, what happens if theta 1 is 0? Well, then you never get anywhere. What happens if theta 1 is 90 degrees? Well, you go high, you get a lot of time, but you don't go far because you got no Vx. Here you got a lot of Vx, but you have no time in the air. All right? So that's one way to do it. Another way to do it is by calculus. So let's check the calculus. Got that? You can pause that, so I'll erase this. And the calculus is like this. I want to maximize this function r, which is my delta x, equal to v1 squared over g times sine of 2 theta 1. And so how you do this, I'm going to let you do this. I'm going to set it up for you. How do you maximize anything? Well, if you set the derivative equal to 0, and of course you might get a min, so you better be sure what you're getting, max or min. In this case, it should be pretty clear. I want to take the derivative of that function with respect to the thing that I'm changing. We're keeping that the same in that. So with respect to theta 1, you might not have thought about that. So you take the derivative and set it equal to 0 and solve for theta 1. And guess what the answer is? You should do this. Theta 1 is 45 degrees. And that'll give you the maximum range. So that's cool. But again, always know to begin at the beginning quick read, slowly sort it, look at your states, decide your coordinates. If I start by projecting horizontally and it never goes up, personally I call down positive. You can also start by projecting downward, right? You can throw the object straight down, you can throw it down to the side, and so you can start it anywhere. If you start horizontally, well, you know that v1y is 0, right? If you throw it horizontally, that's implied. v1y is 0. It's the same as at the top here. But if that's your starting, fine. If you start here, then you know you're down. And then I would call this plus y a y equals to plus g plus x ax equal to 0. Write it. It'll make you clearer. And you're good. And you just proceed. Look at your Vx, your Vy. Look at your delta x, look at your delta y. Look at your t. What do you know? What don't you know? Lay it out. What am I looking for? Range? Yeah, I've done that before, but I'm still going to take these steps. If you jump here, you're going to get flustered, your memory banks will short circuit, and your brain will explode, and you won't have a head. So, or something like that. So do the steps. Trust in the steps. And get them quick, and you're ready for an exam, and you can quickly go one step at a time. So I would say go slow to go fast. Slow and sure, don't miss a beat, and you're rocking and rolling. The same method applies for any constant acceleration equation or problems in 2D. You could be a boat, you could be a car, and in that case, you might not have acceleration in one of the directions 0. There might be a y component, ax component. Fine. Just put it in there and see how it works out. It's a puzzle. You don't know which piece to move first. Just start moving them around. It'll come out faster if you take one step at a time. Write down what you know. Think physics. And trust the method. Know your method. And practice, practice, practice until you get good. All right. Ciao.